let's begin. So last time we were discussing basic combinatorics, right? And the idea, right, is that combinatorics are the techniques for us that allow us, right, to count, which will directly be related to computing probabilities, okay, in an equally likely outcome sample space. But as I mentioned, also combinatorics has wider applications than that, even in this course. So it's actually a crucial topic that will stay with us throughout the course. But so basically, right, there are a few basic principles that we must learn, right, and understand, and then apply that, right, to more general problems. So the first principle, right, is the multiplication principle, which basically says, right, if you choose one item from a set, right, from each set E1 to En, then the number of ways you can do so, right, is the product, K1 times Kn. So the multiplication principle, right, actually, you can say is the mother of them all, meaning that, right, all the principles actually can be seen as kind of like a consequence, okay, of the multiplication principle. The only exception, of course, right, is that, when you have the word or, right, if you choose an item from E1 or E2, right, then, it will be addition or, right, the inclusion-exclusion formula. It won't be the multiplication principle, right? Multiplication principle works with the word and rather than, or, right? But so permutation, right, is an application of the multiplication principle. Number of ways, right, for us to arrange n distinct, okay, items in a line is n factorial, right? And it comes from the multiplication principle because the first spot has n choices, second spot has n minus 1 choices. First spot has n, second, right? And third has n minus 2, etc., right? And so the number of ways, right, is the product of this number of choices. We have to keep in mind, right, that the items have to be distinct. If the items aren't distinct, then, right, the answer is not n factorial, but, right, well, what is it? We'll look at later. But so one common recurring theme, right, in combinatorics is the qualifications, right? It's very important to the correct counting. If we don't describe the qualifications correctly, or we don't have the right qualifications in mind, then the way we count, right, will be incorrect. Example, right, is basically, for example, here, whether you draw 5 cards from a deck of 52, whether you distinguish, right, the suits or not, will result in different ways, different numbers of count, right? All right, so examples of permutation, well, if you arrange an items not in a line, but in a circle, right, then that will result in n minus 1 factorial, right, possibilities or number of ways. The reason, right, is because, you can think of it as like you need to have one item fixed, right, to determine the orientation of the remaining, right, n minus 1 items. Once you fix an item, then the remaining n minus 1 items are just arranged as if, right, on a line. So that's why it's n minus 1 factorial. This one, right, is just another problem, but it demonstrates sort of like you have to be able to view, right, the problem in the right way, whatever that means. So here, right, if you want to keep the couples, right, together, the word together sort of imply that they move together as a unit. So 5 couples have 5 units. So that's 5 factorial, right? And then, but then you have to still look within the unit to see that the couple, right, within each unit can rearrange among themselves, right, 2 ways each, resulting in 2 to the 5th. Okay. All right. And then I guess we ended, right, with combination. We were sort of like discussing combination number, right, at the end of the class last time. So combination is a number of ways for us to pick, right, little k items out of n items, right, without order. Okay. So without order, what does this mean? You know, what it means is like these k items are not then assigned any kind of particular role, right? One way to understand it, right, is that, for example, if I pick 3 students, right, out of 15 students, right, in this class, for example, that's without order because I don't refer to them in any special way. But if I pick them out and then assign like one of them to be, let's say, a president, one of them to be vice president, and one of them be a secretary, then, right, clearly, right, there will be a distinction between these 3 in the sense of which role they take. And that will sort of introduce order, right, among them. Okay. Or like I rank one of them first, second, and third, that kind of thing. So combination, by definition, right, does not have order built into it. If you look at this, right, another way to look at it, right, this definition, or not definition, actually you can argue it out, right, right here, is that, right, n factorial over n minus k factorial really is n minus 1, etc., n minus k plus 1, right? That's this term right here, n factorial over n minus k factorial. That's this. If you look at this carefully, right, this exactly is the number of ways you can arrange k items in a line. Okay, k items where the first one, sorry, k, if you will, sorry, it's not, let's call it k positions. Okay, for position 1, position 2, up to position k, right? Position 1 had n choices, position 2 has n minus 1 choices, and so forth, right? So this exactly are the number of ways you can select k items out of a set of n items where order matters. This is exactly where order matters. Why? Because I say the first position, second position, etc. So the division by k factorial, right, if you will, exactly, right, takes that rearrangement, right, that order out of this count. That's exactly from the permutation principle, right? So that's another way for you to look at it, right? Basically, the combination number, you can see that it inherently takes out the order by dividing by the k factorial, okay? Now, so combination, right, is probably one of the most common concept or tool we'll be using, right, throughout the course, because we're just keeping selecting so many items out of, a group. So it's important to kind of know, right, certain properties. So for example, right, combination, right, number is symmetric, right, because picking k items out of n is the same as leaving, right, n minus k items in the group. The binomial, right, theorem is another application of the combination numbers, because when you expand, right, the n terms in the binomial theorem is exactly like picking k items out of, k, for each of the factor right here, right? It's like picking k x's, right, out of some group, some factor here, and picking that y's, right, from the remaining factor. So that's why it's n choose k, right? You choose which factors to select the x from. You choose k factors, right, to select the x from, and then you choose the remaining n minus k factors to choose the y from. Okay. So that said, right, it's important. Well, not in this class so much because I'm not harping on like numerical answers exactly, but it's still important for you to know, right, basic combination numbers. For example, right, everyone should know, for example, like 4 choose 2 is equal to 6, right? 2 choose 1 is 2. I don't know, right? I think 5 choose 3 is 10, right? Something like that. So where does this come from? Now, of course, right, it can come from the definition, meaning you can write this down. Okay, but this actually is a very clumsy way to calculate because even, right, 5 factorial is 120. So it's a bit large-ish, right? So tool, right, to kind of relate combination numbers, or you can call it a recursive tool, right, to at least in principle allow you to build up any right combination number you want, is a Pascal triangle. Okay, so it starts out with, I guess, some kind of trivial remark that any number choose 0, right, is equal to any number choose n is equal to 1, right? Because there's only one way to choose no item out of n, a group of n, or choose everything right out of group n. So this is clear. On the other hand, right, well, what about this? Again, right, all of this, what we're saying is, well, you can apply the formula and find the answer. Maybe we want to give like a sort of like a combination, right, combinatoric explanation to it. So here, right, well, of course, how many ways can you pick one item out of n items? Well, n ways, right? Item 1, item 2, up to item n. What about this? Well, this you can either use a symmetric principle we talked about here, or, right, again, to choose n minus 1 items out of a group of n is the same as choosing one item to leave behind. And clearly, right, there are n ways to do so. All right, so the Pascal triangle, right, is basically a recursive principle that allows you to build up, right, the combination number. So it starts out with 1, and then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and that's where, right, I got the 6 from, and then 1, right, 5, 10, 10, 5, 1, and so on, right? Well, this is the first layer. This is the second, right? Third, fourth, and fifth, and so on, right? So what this means, right, is, for example, this is 2 choose 1, 2 choose 2, 2 choose 0, 2 choose 1, 2 choose 2, right? 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, right? 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, right? Things like that. So as you can see, right, the way, right, the triangle is built up is if you add, right, any numbers here, you get the next one, right? 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, 1 plus 3 is 4, right? So on, okay? And it's encoded like this, right? N choose k minus 1, n choose k is n plus 1 choose k right here, right? 3 choose 2, sorry, 3 choose 1 plus 3 choose 2, or I guess here, right? I was demonstrating this. 4 choose 2 plus 4 choose 3, I guess here, right? 4 choose 2 plus 4 choose 3, right? 6 plus 4 is 5 choose 3, which is 10, all right? And so basically, right, this kind of, again, right, explains how you build up the Pascal triangle, right, which is something you just kind of need to know when you look at combination number. Well, it remains to explain, right, why this is true, right, how this is true. Again, right, you can kind of prove it by, I don't know, right, the definition, but that's a clumsy way to do so. We want to explain it kind of using counting intuition. And this actually will, the explanation is actually very similar to the problem, right, we were doing last time, which is this, kind of a group of friends, and you try to, invite, right, decide whether or not you can invite these 2 special friends, right, to the party. The reason, right, is here. Well, when we look at n plus 1 choose k, right, what happens is you can look at it as a group of n items. Right, you have n items like this, and you have a 1 special item, okay? So out of these, right, you want to choose k items. That's n plus 1 choose k, all right? Well, how can you do so? Well, there are 2 ways you can do it, right? Not 2 ways, but like 2 possibilities, okay? the first possibility is your k items come entirely from this n items. That's n choose k, right? So you can have n choose k, and that gives you the entire k items. Or, right, you can choose one item from here, right? And that's only one way to do so. And the remaining k minus 1 items come from this group. And of course, right, together, that will tell you the total number of ways you can choose k items out of n plus 1 items. So that's why these two are equal, right? Like that. Okay. So, but like I said, right, in terms of recursion, right, it tells you how to move from layer n to layer n plus 1, right, in terms of Pascal triangle. All right. Any question about this? All right. Well, I guess we can take a look at that later. That's a fun kind of exercise in combination. But let's finish, right? Let us finish this problem. Okay. And then we will go back to combination. All right, so we were right at part A, where right, so we decide how many ways we can invite 5 friends to a party, but the some two special friends, right, not attending together. So this problem at first read, right, can be, let's say, not easy to approach if you don't have a clear picture in mind. So it's kind of talk about combination, right? But you kind of have to see where you're picking things from, okay? And that's what the problem doesn't spell out for you, or like you have to, right, have that kind of built in for yourself, right? So when it says 8 friends and 2 of them have something special going on, so what that means is actually this group of 8, right, actually should be visualized as a group of 6 and a group of 2. Okay, these are 2 feuding friends right here. All right. And out of this, you pick 5, right? Because you invite 5 to go to a party. So you're picking 5 out of 2 groups, right? But depending on how you split it, right, that will accomplish whatever you want to do. So here in part A, you want to pick it so that, right, the 2 friends are not attending together, right? So there's an excellent way to look at this, as one of you guys, right, proposed last time, by looking at it as the complement, right, count. Meaning that, right, instead of counting the number of ways the 2 friends not attending together, let's count the number of ways the friends attend together and subtract that from the total number of ways, right? That's an excellent way to look at it. That's counting by complement, and that exactly is, corresponding to the way we calculate probability by complement. But again, right, with this picture, right, how many ways can we invite, right, 5 people to a party if the 2 will attend together? If the 2 attend together, right, then this 2 will, right, so this is a group of 5, right? That's a party for us. If the 2 must attend together, they will come in here, right? No choice. There's no choice for that, right? That means we only have 3, right, left to fill, right, for this party of 5, and this 3 must come from the 6. That's why 6 choose 3. All right. So that's counting by complement. Now, what about counting it directly? If you want to count it directly, right? Again, which one's easier? Which one's harder? The direct count, we'll have to go through cases, right? Because clearly, right, if 2 of them do not attend together, there are 2 cases. Either none of them come or one of them comes, right? So it's sort of like tedious from that point of view. But it might be a little bit more natural, as in like we tend to think positively than negatively in terms of complement. Does it matter in the end what answer you get? No, right? Whichever you get, that's correct, that's fine. And you should actually train yourself to be able to think in both ways. Because actually, right, thinking in a complement this way actually is an excellent technique. Like I said, right, because we tend not to think in that direction. But Okay, how to count directly, right? So how to count directly, we have to go through cases, right? So the first case is that, none of them, right? None of these guys attend. That would satisfy that, right? So, well, of course, if none of them attend, then you have to fill all the 5 from this group of 6. So that's 6 use 5, right? Or, right, you only pick one of them, right? You fill in only one of them. But of course, right, that will leave us with, right, 4, right, to fill in from here. So that's 6 use 4. All right. Now, as with any problem, right, there are multiple ways to solve it, but if you get the right solution, then all the right solutions must get the same answer. And so, right here is worth our time, right, to demonstrate that these are actually the same count. Well, how? Well, by just seeing what that is, right? And this actually also demonstrates, the use of Pascal triangle, because now we need to know, right, what these numbers are. So I guess, I guess it goes to 8. So who knows? But so the Pascal triangle, right? 1, 5, 10, 1, 5, 10, 10, 5, 1, right? Is the layer of 5. 1, 3, 3, 1, 1, 4, 6, 4, 1. Yeah. All right. So this is layer of 5. So layer of 6 will be 1, 6, 15, 20, 15, 6, and 1, right? So 6 use 5. This is 6 use 6, right? So 6 use 5 is 6. 6 use 4 is 15, right? So the answer here is 21, right? So the answer to A, right? Not that I care for the final answer, right? This is fine. It's 21. Well, is this 21 too? Let's verify, right? 6 use 3, 6 use 1, 6 use 2, 6 use 3, right? So 6 use 3, 15. All right. What about 8 use 5? Well, 8 use 5, I either have to go build, next 2 layers, or I just do the formula. I think I'll probably do the formula, right? What's 8 use 5? 8 use 5 is 8 times 7 times 6 over 5 factorial, right? Which is 120. Well, 120, I can cancel the 6 out, right? Give me 8 times 7 over 20. I can cancel the 4, right? Giving me 2 times 7 over 5. Wait, that looks weird. What did I do wrong? 8 use 5 is 8 times 7 times 6 over 5 factorial. This looks, I make a mistake somewhere. Where did I make a mistake? 5 factorial is 120. 1, 2, 3, 4, 5. That's correct, right? 5 factorial is 120. Hold on. 8 use 5. This is correct. 6 cancel with 120, give me 20. Cancel with 4, giving me 5. But why is this not correct? So is 5 factorial is exactly 120, right? 2 times 3 times 4 times 5. Yeah, this is 120. That's correct. And then if I cancel the 6 out, I get 20. I cancel the 4, 5. But this is not. Hold on. What did I do wrong? Is factorial over 3. Oh, sorry. Over 3 factorial. Sorry. This is over 3 factorial, not 5 factorial. Sorry. This is over 3 factorial. So this is going to be 8 times 7 times 6 over 6, right? 3 factorial is 6. So that's going to be, sorry, 6 cancel with 6. So that's 8 times 7. So that's going to be 56. All right. So, and then 56 minus 15. I guess I'm still wrong, right? So 56 minus 15 is 41. So this is embarrassing. Did I still do something wrong here? Oh, sorry. This is incorrect. I forgot this. If right, if I choose, I can choose all 5 to go from here. But if I choose 4, right, there are 2 ways for me to choose the one friend. So this is times 2. Sorry. All right, times 2. So 6 choose 4. 6 choose 1, 2, 3. Hold on. 6 choose 4 is 15, right? So 15 times 2. So that's 36. Hold on. I seem to be making mistake here. I apologize. Let's see. 6 choose 5. 6 choose 4 times 2. That's like that. 30 plus 6 is 36. All right, I give up. Let me take a look at the solution and see what mistake I made. This is that. That's correct. That's that. So this is exactly the solution. So why did my calculation go wrong? A choose 5 is a factorial, 3 factorial, 5 factorial, which is 8 times 7 times 6 over 3 factorial, 3 factorial 6. So that's 56, right? And 6 choose 3 is, 6 choose 3 is 1. 6 choose 0, 1, 2, 3. 6 choose 3 is not 15. 6 choose 3 is 20. All right, and that's 36. Yep, all right. So yeah, the answer to both of them is 36, all right? But yeah, anyway, right, sorry for the fumbling. But so basically, right, both both ways of counting, right, gives the same answer. But well, as I demonstrate, right, it's good to check the numerical answer in case you forget your, sort of like count somewhere. And also, of course, right, there's mistakes you can make along the line to get the count right. But so apologize for that. Any question about part A here? All right. So I guess let's move on to part B, right? And then we'll kind of go back and do the other example of combination. But part B asks how many choices can we make if 2 of the friends will only attend together? Or what would the answer be?
The answer is 6 choose 3.
Yeah, right, exactly, from part A, right? 6 choose 3, correct. Oh, sorry. So the way you read part B is this. So you invite 5 friends to a party, right? You can, if 2 of them will only attend together, then you either invite both of them or you can invite none of them, because this is up to you, right? So it's not like you have to invite them. Does that make sense? So part B has that flavor too. So how many choices so part B means this. Well, it's up to you. But if you invite, then you have to invite both of them. Does it make sense? Or you don't have to invite either of them. If you don't invite either of them, then the answer will be
6 choose 5.
correct. So that's the answer to B, right? Where it also note the option that, you don't have to invite either one of them. All right, any question about this problem? All right, so let's kind of go back and do some examples of combinations before we continue with the problem. And right, so this right here, right, is sort of like a classical example in, so-called a game of poker, right? Not that, we will look at poker too much in this class, but and not that you need to know the poker lingo either. We'll explain it, right? But basically, like, it's sort of like, I don't know, a time-honored tradition for some reason that, every time we go, we talk about combinatorics and we talk about deck of cards, then, sort of like poker, right, is the poker hands is the sort of like the classical count. So let me explain, right? So basically, the poker hands, right, is as followed. You select 5 cards, right, out of deck of 52, similar to what we talked about before, right? But now you look for, like, pattern in the card, right? And then you kind of like rank them in terms of rarity. Basically, the idea is like the hand or the pattern, right, that's more rare will beat, right, the one that's less rare. So the order is as follow, right? Of course, there's kind of the no pattern, but we're not going to look at that. But it goes 1 pair, 2 pairs, 3 of a kind, straight. And here, let us kind of like say, this is not technically correct, but it makes the count easier. Let us include the straight flush in here as the count. But technically speaking, the straight in a poker hand does not include straight flush. Straight flush will kind of like is a category on its own. But here, when we count it, we'll include it just to make things easy. Straight, and then flush, full house, 4 of a kind, and I think both that is straight flush. There's a royal flush, but there are only 4 types, so we're not gonna go there. All right. So the idea, right, is as you go along this, you get is more rare, right? As you go down this way, and so, right, if you get a full house, then you will beat anything below that. All right. So remind ourselves, right? Basically, right, a deck of cards has 13 denominations, right, from ace to 3, etc., right, up to 10 jack, king, and queen and king, right, and 4 suits, right, club, diamond, heart, and spade, right? Of course, there's 2 colors, but let's not worry about that. So basically, right, the pair here refers to, out of the so you have 5 cards, right? One pair, well, kind of hopefully explains itself. That's exactly, you have 2 cards of the same denomination. Or you know what? Basically, let me just give an example that's easier. So a pair would be something like this: ace, ace, let's say 10, jack, and let's say 8, right? So here you have a pair of ace, right? Like that. And also, right, you probably quickly notice that here, let us also count it where order among the card not matters. Okay? Because basically, if we could build order into here, but let's just make it more natural that way. That basically, when we look at the cards, right, out of 5 cards, like the ace doesn't have to be like the first card's going to be ace or second card, that kind of thing. They can be anywhere, right, among this pair this 5 that pair of ace shows up. So that's just the way we decided, right? You can count it using order matters, and I will explain like the difference. But here, right, let's just keep the count, that order among the cards. The 5 cards doesn't matter. So 2 pairs, right, would be, of course, something like king, king, right? I say 9, 9, right? And then let's say 2, okay? So this is 2 pairs, right? A pair of king and a pair of nines. Again, right, notice, of course, right, this can come from any suit, right? 3 of a kind, so I don't know, right? 8, 8, 8, and like a 4 and a jack, right? Straight would be cards that are consecutive in order. For example, 2, 3, 4, 5, 6, right? Any suit will be an example of a straight. Now, the thing you want to pay attention, and just sort of convention of poker, ace counts as 1, so this is a straight, but also counts as, I don't know, the 13 cards. So 10, jack, king, queen, jack, queen, king, ace is also a straight, right? So in this sense, right? So I guess ace here count as a 14th card. We also serve as a first card. So, both of these count as a straight, okay? Flush is, when all cards have the same denomination. Same suit, right? Whatever the denomination is. Okay, so all cards of heart, all cards of spade, all cards of club, that kind of thing. Okay, 4 house is basically 3 of a kind plus a pair. So something like king, 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 10, 10, right? That's 4 house. 4 of a kind, again, that's self-explanatory. 9, 9, 9, 9. Let's say an ace. Straight flush, again, self-explanatory. Straight and a flush. So basically, you have a straight, but also of the same, right, suit. Again, right, these counts don't matter, as in like we're not gonna sort of deal with them a lot in this class or at all in this class. But like I said, right, it's a time-honored tradition, so why not? It's kind of fun, it's in movie and stuff also, right? If you pay attention to this, it does show you or hopefully illustrate, right, techniques of counting and how combination works and things like that. So it's actually educational too, well, not in a gambling way. But all right, any question about what this mean? The hands.
Am I allowed to ask if you gamble, Professor?
Yes, you may. I used to do it when I was young, no longer.
Okay.
And by gamble, I don't mean like gamble. I just play with friends. But yeah, I do play. I did play.
Got it. Cool. Thank you.
Yep. So yeah, I did play poker, but not very good at it. All right. So cool, right? Let's start. So let's start with 1 pair, right? And here, note that we're not counting the probability, all right? We're just counting number of ways we're gonna get 1 pair. And of course, right, by the way, we're talking about these things, you'll see that basically, right, the count will get smaller and smaller, right, as we go down, because it's gonna be more rare, all right? So And actually, right, in fact, maybe the counts down here will be easier than the count up here because, you know, you have to look at more possibilities. But anyway, right, let's start from the top. You know what? Who knows? Maybe actually from that point of view, maybe let's start from the bottom, maybe? Who knows, right? Because like I said, there are less ways here, so maybe it's easier. All right, let's maybe start with this. How many ways can we get a straight flush? No, that's not too easy. You can move to the four of a kind, but how many ways can we get a straight flush? Well, let's ask a different question. How many straights are possible? How many types of straight are possible?
Would it be 14 maybe?
Not 14.
I think
You start out
13.
with not 13. That's too many, right? You start out with what? The smallest straight, if you will, is ace to five, right?
Okay, so 9,
10,
10.
because the largest is 10 jack. So look at ace to 10, right? So 10 types of straight. Agree? The smallest.
But would it? Oh, sorry.
Go ahead. Yeah.
I thought like queen, king, ace, 2, 3 would
Oh, it
also
doesn't go.
be.
Sorry, it doesn't go like that. Apparently, you don't play
Oh,
poker.
okay.
Sorry, I don't mean anything by that. Sorry, it doesn't. It doesn't cycle back. It does not cycle back. This is the largest. Yeah, yeah. No, good question. No, yeah. So ace start as the smallest number and also the largest number, but no, you don't cycle after you touch the ace. From there. Sorry. Yeah, I guess I took it for granted. No. Yeah. So that's it. That's it. Sorry. So 10 types of straight. Is that clear? Right? Smallest is ace to five, largest is 10 to ace, right? So 10 types of straight. But if you insist that they're all of the same suit, then there are four suits, right? For each side of straight. So in total, we have 10 times 4. Correct? So only 40, right? Possibilities for straight flush. How many four of a kind can we get? How many four of a kind can we get?
Would it be like 13 for the like four of a kind um times 4 for the different suits you can have, and then for the last one like times 48?
So you're almost correct, except I don't think, right? First of all, if it's four of a kind, there's no suit because they're all just all the suits are there, correct? So
Yeah.
out of 13, you can do this. Out of 13, you choose one for the denomination of the four of a kind. That's it. Because that's it, right? Once you choose that, then they all have to be present there. And then, right, your 48 can be answered as 12, choose one. Out of the remaining denomination, choose the one denomination for the loan card. And now the suit is for that card. But I think you said 48. So yeah, right. There's no
Yeah,
suit
so
for this.
I just multiplied for one more time. Yeah, that makes sense.
Right. So basically, it's 13 times 48. But yeah, we don't care for the answer. Again, right? A theme that will go forward in this class is I don't care for numerical answer explicitly, but symbolically, or like this, right? The answers like this, as you can see, right, is much better because it explains how you count, how you think, right? What the formula looks like. Okay. All right. Any question here? All right. Full house. How many ways can we get a full house?
Uh, 13 times 4 choose 3 times 12 times 4 choose 2.
Excellent. I'll just do a 13 choose 1, right? Just out of principle, but
Yeah.
you're correct. Like that, right? Correct. Right. So explanation, right? First, you choose the card for the triple, right? For the three of a kind. And then, right, out of the 4 suits, you choose the 3 cards, the 3 suits, right? That goes in for the three of a kind. And then out of the remaining 12, you choose 1 card for the pair. So the 1 denomination for the pair. And then, right, out of the 4 possible suits, you choose the 2 possible suits for the pair. So that explains the count. All right, any question? Again, right, as you should note that as we keep going up like this, the number starts to be larger, right? Okay. And you can check my correctness, if you will, right? If you care, is you can take all these numbers and you can divide by 52 choose 5. And you'll see the probability of these things, which, right, should be listed on the internet. So but if you care for, we're not getting there yet, but that's how you get the probability of this. All right, flush. So let me just write down here, right? Flush.
I think that would be 13 choose 5 and then times 4 for each suit.
Correct. That's excellent, right? So they all have the same suit. So let's go like this. 4 choose 1 first, right? 4 choose 1 means what? Out of the 4 suits, you choose the 1 suit for your flush. But once you have the suit, right, then that suit has 13 cards, 13 denominations. So you have to choose out of 13 denominations, you have to choose 5, right, for your cards. All right. Any question? Okay, so now for the straight, let us do it correctly, right? And not include the straight flush. Because right now that we count as straight flush, we don't have to include it. All right. How many ways can we get straight?
Uh, 9 times 4 to the 5, fifth power.
10, right? Not 9,
Oh,
because there are
10.
10 ways to get it straight. Yeah,
Oh,
very good. So 10, right? Because there are 10 ways to get it straight. But now we're not limiting the suit. So each of the card can be a 4 suits, so it's 4 to the 5th, right? But let's subtract 4 times 10 because we don't want to include the straight flush in there. Is that okay? Okay. 3 of a kind.
Wait, I'm sorry. How'd you get the 4 to the 5th here? I don't understand that part.
Sure. Like look at 2, 3, 4, 5, 6, right? Now we're not limiting which suit each of the card is, as long as right they form a sequence. So 2 has 4 choices, 3 has 4 choices, and so on.
Okay, I got you. Thank you.
3 of a kind.
know if that's, I don't know if that's
Would that just be 13 choose 1 times 12 choose 1, or 13 choose 1 times 4?
it makes sense that there's more though, but
Sorry, which one?
So like
Multiple people are speaking. Are we talking about the same 3 of a kind, or was
sorry.
there a question for something else?
Yeah, so 13 choose 1 times 4. So
Times 4?
or no, times 4
So-
choose 3.
Yeah, you're working on the 3 of a kind. That's correct. Okay, good.
And then the next one would be like 12 choose 1 times 4. So plus, so like times 4 choose 1.
Hmm.
And then the next one would be 11 choose 1 times 4 choose 1, I think.
Right. Yeah. So this right addresses the 2 lone cards, right? That's very good. But there's a subtle error here. It's very good. Almost there, but there's a subtle error. And actually it's easy to make this kind of error. All right. And let's see if anyone spot the error. Or right, actually, since it's 53, I'll say that in principle, this is almost correct. The error actually is somewhere else, right? It has to do with our assumption.
There's no order. Oh yeah, yeah.
Right. So, we will go back to this, right? And I'll point out the subtle error. It has to do with, right?
Do you
Going
have to
forward.
subtract the full house?
No, this actually will not do the full house because the reason is when you do 12, 11, you already make sure the cards are different. So no, this does not overcount full house. That's not the subtle error.
Okay.
Unlike the straight flush, the straight includes straight flush in this count, so you have to subtract. This does not include the full house because you do 12 and 11. So you already make sure the 2 cards are different. The subtle errors has to do with the order. Okay, I'll explain it. But for now, let me move to the quiz, and I will address that right after we come back. So the quiz, of course, is this problem. Okay, so there you go. That's the quiz for today. And just a reminder, right? So there are 2 questions. Starting from today, going forward, the quiz will be graded on precision. All right, you have to get it right to get credit. Okay. Any question before I turn off the volume, the audio and video? We'll start at 6.5, or rather 7.5. Okay.
Professor, could
Yeah,
you
go ahead.
scroll up a little bit? So it's like
Sorry. Yeah, you mean like kind of like blow it up a little
Yeah,
bit?
yeah.
Yeah,
Oh,
because
a
the answer
little
is
bit
right there.
more.
So, okay, is that helpful?
A little bit more.
A little bit more, huh?
Oh, there we go. Okay.
But then I think it's blocked, right? Y-
I get what you mean.
Yeah. So like that. Is
Uh,
that
yeah,
okay?
that's fine.
Okay.
Yeah.
And Professor, you didn't specify A or B. We're just doing the whole thing.
Your whole thing. Yeah.
Okay,
Just write
thank.
out the answer. No need for numerical answers.
Okay.
Yeah.
Professor,
Yeah. Was there a question?
Oh yeah, you said we don't need to show like the numerical result,
No,
right?
no. Just the combination numbers is all I need, even for the exams. Okay. I don't need
Okay,
numerical answers. I only need numerical answers to show you that they're equal. Yeah.
I see. Thank you so much.
Mhm.
All right. Is there any question before we continue?
Professor, I think I had some trouble
Yeah.
submitting it.
Then send it to me by email, but try not to, try to solve that
Yeah.
problem next
Okay.
time. All right.
I'll send it
Because
like right now.
okay,
Okay,
cool.
thank you.
Thanks. Mhm. All right. So yep. So back to the right discount, and let's try to address right. This discount, right? So again, right, the spirit of this count is correct in the sense that, right, first you choose the denomination of the three of a kind. Out of three suits, out of four suits you choose three, right, for the three of a kind, right? Out of the 12 remaining denominations, right, you choose one for the loan card. But you see here, this is the clue. You almost want to say you choose one for the first loan card, and that's a clue where things are where you are building order into the account, right? Because here, right, you kind of see naturally you want to say out of the 12 denominations, use one for the first loan card, and out of 11 remaining denominations, choose one for the remaining loan card. And exactly right here is where you build order, right, into and by the way, right, you build the order into only the two loan cards and not in the three of a kind. So first of all, right, it doesn't follow what we're wanting to do here, where we say order not matters. But even if you say order matters for some reason, you want to count this where order matters, which right will make all this count much more complicated. Whoever's not turning off the microphone, please turn off the microphone. All right, so right, but even if you want to say order matters, which will make all this count much more complicated, then this is still not correct, because right here, when you count this, you don't put order into the three of a kind. So that's why, right, this count is, let's say, okay in spirit, but certainly not correct. Okay. And let me just say one more thing. And where does this come from? This comes from, of course, the multiplication principle. And so when you use the multiplication principle, right, be careful that you may, let's say, unintentionally, unconsciously, right, introduce order into your count. But it depends on the cases, okay? Because, for example, right, let's take a look at the prime example of the multiplication principle, right? Here, right? How many ways can we choose to set up meal like this, right? And this 3 times 6 times 5. Let's ask the question, is there any order in this count? Is there order in this count or not? The answer is no, right? There's no order in this count. What does that mean? What that means is you could put the main course before the appetizer, right? Before the dessert, whatever. But in here, we're just building up a meal, right? With these three courses. And there's no order like built into this count. When will order be built into this count is when you kind of say, well, I want to also take into account how you eat the meal. Like say some people want to eat dessert first and appetizer last, that kind of thing. But if that's the case, then actually you have to multiply with 3 factorial, right? To put that weird order into it. But in this way of counting the multiplication principle, no order is built into it. And I guess one way to explain it is because the sets are different. These are different sets, right? You pick one item from a different set, a different category. All right. But here, when you do the permutation, then you also use the multiplication principle, but you have order built into it. And why so? The reason, right, is because when you do this, you set first position, second position, and so on. The first position has n choices, second position has n minus 1 choices. So that's the best I can put it, right? You have to look at, when you count, are you saying that language? Are you saying the first one is this, the second one is that kind of thing? If you do, you have built a position in, you have built order in, because you have said first and second, right? But if you don't, let's say, right, this, well, because, right, a meal is a meal, right? Wherever you put the appetizer and stuff like that. So this has no order, right? So sometimes, right, the multiplication principle includes order into the count, sometimes doesn't. You just have to watch it when that happens. All right. But here, in this count, you introduce order into this count because, right, you said the first loan card has 12 choices, second loan card has 11 choices. All right. And so how to correct it? How to correct this count? You can correct it by simply doing 12 choose.
Divide by 2.
Yeah, or you can, but that's a bit, let's say, less intuitive. You do 12 choose 2, right? I mean, of course, it's divided by 2, but 12 choose 2, right? And that explains it. Of course, this will be squared, right? Why? Because, right, now the explanation is very simple, right? That basically, right, out of 13 cards, 13 denomination, choose 1 for your 3 of a kind. Out of the 12 remaining denomination, choose 2 for your 2 loan cards, right? Notice this will ensure that the 2 cards you choose will be different. 12 choose 2, right? By definition, will choose 2 different cards, but also it will not have order in it. Okay, of course, you can do the other way and divide by 2. Any question? Okay, so let's do 2 pairs. How many ways can we have 2 pairs?
Will it be 13 choose 1 times 4 choose 2 times 12 choose 3 times 4 cubed?
12 choose 3. Is that 1 pair or 2 pairs we're talking about?
2 pair.
Okay, so say again, 13 choose 1 times 4 choose 2. Okay, and then 12
And then
choose 3, you said?
choose 3, yeah, times 4 cubed. So 4 choose 1, yeah.
Yeah, wait, I'm still not following because it seems like you're looking at one pair here, not two pairs. Why would this be two pairs?
Um, because you're choosing one denomination for the pair, and then you're choosing two suits, and then the other three cards don't matter.
So that's one pair, right?
Oh, my bad. Right. So
Yeah, I keep asking.
this would be one pair.
No,
Oops.
so this is correct. This is correct for one pair. That's correct. But yeah, we're looking at two pairs. So no, it's fine. You're doing one pair. Yeah. So two pairs is
I'm guessing it would be so 13 choose one times 4 choose 2, and then 12 choose 1 times 4 choose 2, 11 choose 1 times 4 choose 1. But I'm guessing we're gonna have to like divide by something if about the order
yeah,
maybe.
right, because here you introduce the order between the pairs.
Yeah.
So actually, right, 13 choose 2.
Oh, right. Yeah.
That's it, right? And then times that.
Okay, that makes
So
sense.
right, yep. You choose two denominations for the pairs, and then each of them, right? This is the suit, and then that's the loan card. Okay. Right. Any question about this count in general? All right. So, like I said, right, just kind of like a fun exercise, if you will, right? In counting and combinatorics and whatnot. We won't see this too much in this class. All right. So let's look at this question, right? This is kind of like a example that shows up quite often, right? Where we do a lot of problems where we pick balls some urns, and you know you have to distinguish where where you sample without replacement or without replacement, that kind of thing. And I guess here, right, it's a bit ambiguous on the order. So let's say, right, order does not matter. Okay. Again, I'll explain, but here it's not specified in the problem, but say order not matters. How many ways can we do this? This should be much easier, right? The answer is 5 choose 2 times 10 choose 2, right? Is that okay? All right. So let's take a look at the next question in our problem set. Which is this one. Okay. And let's give it a minute and then see if anyone has some input on what the answer should be. right? So I guess, right, so here's A and here's B, right? And a path, right, would go through the grid points, right, but can only go up and right. So this is a possible path. This is another path, right? Yet another path, and right, something like that, right? So how many paths can there be in total? So, right, look at the hint here. What is a path? What does a path consist of? Might look bizarre, right? Or might look sort of random or arbitrary, but it's not, right? A path is very much well defined. You have to take exactly 4 steps to the right and 3 steps up. So I guess there's still some arbitrariness to it, right? But where is the arbitrariness? Where does the arbitrariness come in? Okay. Any input before I tell you the answer?
I think it's 7 choose 3.
That's correct, right? Or 7 choose 4 for that matter. Right. Okay, very good. And the answer comes from where?
So you're always taking 7 steps in total, and you're just like sort of like choosing which of the 7 like you're like planning to make it going upwards, or like that you have to have 3 steps upwards, so you just choose 3 from the 7.
Yeah, no, yeah. So that's roughly it, right? So if you write down, right, the sequence of steps, it'll be something like U for up, right? R, U, R, U, R, something like that, right? 4 steps to the right and 3 steps up. So if you look at it from this way, right, it's going to be a sequence of 7 letters, right? Where 4 of them must be R and 3 of them must be U. And right, a path will be exactly where, right, you place the U's, and then the R's, right, will be kind of in the remaining positions. And so basically, right, it's really about out of 7 positions, you choose 3 positions for the U's, or for that, you know, equivalently, right, you choose 4 positions for the R's. Now, right, let's kind of also comment on, right, why is 7 choose 3 and not something like 7 choose 3 times 3 factorial, right, where order matters. So here order does not matter because, well, you see, right, up is up. There's no, right, switching around the ups, and that results in a different path. All right, so that's why, right, this is 7 choose 3. Or again, 7 choose 4. Right. Any question about this? Okay. So, well, I think this is easy, but let us talk a little bit about the next slide before we continue. All right. So we kind of like mentioned this already, right? But sometimes, right, you want to choose a set of k items out of a set of n items, but order matters. Okay, so again, I guess the more important question here is, do we know when? And it's hard to tell, right? A lot of times it comes from the context of the problem. Like basically, the context of the problem kind of dictates that here, when you select, the items out of the group, the order matters, right? So, for example, like I said here, if you choose 3 students out of a class of 44, then order does not matter. But if you choose and then you assign rows to them, then order matters, right? So that's the only remark, because the count is actually easy. If you know the number of ways, right, to count where order does not matter, then you just have to compensate, right, to get to the order matters. Or, right, vice versa. This actually, right, like I said, is also n times n minus 1, n minus k plus 1. So it doesn't matter, right? I think this way of writing is kind of preferred because it's more compact. But, right, so this is sometimes also called the permutation number. But, right, I mean, NPK, right? But, we also refer to the permutation as this, right? And actually it's consistent because n factorial, as you can see, is something like NP1, right? But doesn't matter, right? So here we just kind of mention that, right? This is a number of ways to choose when order matters. All right, any question? Okay, so let's take a look at number 4, okay? This may or may not have anything to do with what we just discussed. I just want to discuss that slide, right? But let's take a look at number 4 and then see if anyone has an input to the answer. Okay. Any input on what the answer should be?
But 3 factorial times 2 to the 3rd power.
Correct, very good. So this actually is just kind of like another way to, similar to the couple question, right? Basically, the twins have to stay together, so they move together as a unit, right? That gives us 3 factorial ways, right, to arrange this 3 sets of twin. But within the room, right, they can switch beds. So, right, that's 2 cubed. Right? Any question here? Okay. All right. So this is the last one, I think. Hold on. No, not yet. All right. So for the last 2, let's talk about the next concept. All right. So the concept that's also equally important here, right, is the multinomial coefficient. And so the first meaning of the multinomial coefficient, right, is basically choosing more than one group, right, out of a big group. What does that mean, right? So basically, right, n choose k, right, the binomial coefficient can be thought of, right, as, well, you divide your group into 2 groups, right? A group of k and a group n minus k, right? Again, where order does not matter, but you just count number of ways to divide your group into k and n minus k items. But then, right, that doesn't have to be the end of the story. You can divide n items into m subgroups, right, with these relative sizes. Of course, right, the size of the subgroups must add up to the size of the big group, right? So, but the question is, how can we do that, right? Or how many ways can we do that, right? And the notation for this is, right, n choose k1, k2 up to km, right? So yeah, right. So I don't know, right? Instead of picking 3 students out of the class, I can pick 3, and then I can pick 5, and then so on and so forth, right, until I exhaust everyone. And so the number of ways to do so, right, is actually rather simple. First, you choose k1, right, for the first group, and then of course you have n minus k1 left, right, and then you choose k2 for the second subgroup, and then so on, right, until, of course, right, the last remaining one is km remaining, and you choose km out of this. And that's just explaining it by multiplication principle, right, and combination. But if you write this out, you will see that this is n factorial, right, over k1 factorial, n minus k1 factorial, right? The next one we have n minus k1 factorial over, right, n minus k1 factorial times n minus k1 minus k2, right, factorial. So you see, right, first of all, the n minus k1 factorial here will cancel, right, like that. Okay. Oh, sorry. This is not n minus k1 factorial. K2 factorial, right? K2 factorial, right? Because it's n minus k1 choose k2, right? So n minus k1 factorial over k factorial. So this cancel with this. But if we write this term out, right, you see that the next term will have n minus k1 minus k2 factorial on top, which will cancel with this, right? And so basically you see that all these terms cancel, leaving you with n factorial, right, on top, and then k1 factorial, k2 factorial, all the way to km factorial at the bottom. And so, right, that's the multinomial coefficient for you. Okay. And so again, right, the meaning of it is that, right, it generalizes, right? It generalizes the binomial coefficient because, right, if m equals to 2, right, meaning you choose n, choose k1, k2, well, of course, right, k1 plus k2 is equal to n, or k2 is n minus k1, then this is just a binomial coefficient, right? So binomial, right, is when you choose it to two subgroups. Okay. And there is the symmetry here, where, right, you can just basically, right, it doesn't matter how you arrange the subgroups, the number of ways you can divide this, right, into the subgroups, as long as the sizes are the same. That's what we mean here, right? These are any permutation of this number. So basically what we're saying is this, right? Let's say 4, or rather, right, let's say 8 choose 2, 2 and 4, let's say 2, 3, so let me do 9, right? 9 choose 2, 3, and 4 is equal to 9 choose 4, 2, and 3. All right. I mean, if you say it this way, it's almost obvious, right? You try to divide 9 to a subgroup of size 2, 3, and 4, right? So of course it doesn't matter how you write it. But and also there's a multinomial expansion that goes with this. Again, the reasoning is the same as the binomial expansion. We're not gonna kind of use this, so I won't really harp on this. But yeah, right, let's look at this example. If an urn has 4 blue, 7 red, and 8 greens, right, and you pick, right, 7 balls, so that 2 blue, 2 red, and 3 greens, right, coming out of these guys, right? How many ways can you you know what, I think this one is not really a multinomial coefficient. This is 4 choose 2, because out of 4 blue you choose 2 blue, out of 7 red you choose 2 red, out of 3 greens you choose, out of 8 greens you choose 3 greens. Sorry, this is not an example of multinomial coefficient. I think I should include it here. I'll take it out, right? Sorry. But so yeah, so the message is just here, right? The multinomial coefficient, like this, right? It's a way to generalize, right? The binomial coefficient, or the combination number, right? Where you choose, instead of choosing one group, right, you choose more than one group out of a big group. Okay, so that's one reason why you should care about this number, because it kind of generalizes, right, the binomial coefficient. But here's another reason why, and this is actually maybe equally important, right? Remember, right, I kind of talked about, right, how many ways, right, for you to, let's say, permute numbers, right, on a straight line, but if items are not distinct, right? So if you have the n items arranged in a straight line, but they are not distinct, then how many ways can you do so, right? For example, right, if you have, like here, this example, if you have 14 items in total, right, 4 of them being blues, right, 4 of them being reds, and 6 of them being greens, and you arrange them in a line, then how many ways can you do so? Notice, right, clearly, right, as this example seems clear, this is not 14 factorial, right? Because if you permute the blues among themselves, you're not going to get anything new. But, right, this actually should look suspiciously similar to the upright, right? The sequence of, paths, right, that we look at here. This exactly has that flavor, right? Where you see, you have the sequence of U's and R's, and you can permute the U's and R's, but the U's are identical, right? And the R's are identical. So in general, right, you see the principle is, if you want to arrange, right, items in a line, but the items are not distinct, right? They form some kind of groups, right? Then their permutation, right, will kind of like boils down to the positions of the identical items, right? For example, remember, right, when we look at the UU, right, UR, that kind of thing, right? What matters here is where we put the U's. So that's why 7 choose 3, right? Because once you pick the positions for the U's, the U won't permute among themselves, right? Because the U's are identical. So same thing here, right? If you want to look at this problem where you have the blues, the reds, and the greens. So what happens is, right, the number of ways you can permute this around is, out of 14, you have to choose the position for the, let's say, the blues first, right? And then at the remaining, you have to choose the position for the red, and then at the remaining, you choose a position for the green. But, right, a different way for you to say that is, of course, right, out of 14, you choose 4 position for the red, so 4 position for the blue, 4 for the red, and 6 for the green. So it's the multinomial coefficient. Does it make sense? So the multinomial coefficient, right, or, as you can see here, right, the binomial coefficient, as a simple example, will give you the number of ways to permute items on a straight line where the items are not distinct, or where the items can be identical. Okay, any question about this? All right. So now let's take a look at this question. Oh, sorry. All right, and I think there are 2 questions here, okay? And note that, right, this question has this phrasing. All right, and so I'll give you a minute or 2, and then we're gonna address the or try to see if you have any input to the answer. All right, so let's address the first part, which is right this sentence right here, right? Scoring takes account on the country, but not the individual identities, right? What does that try to refer to in terms of counting? Or in terms of combinatorics, what does that try to tell us? It tries to tell us, right, that the lifters from the same countries are indistinguishable, right, or non-distinct, or lifters from the same country are identical, right, because you don't take account of their individual identities. So again, right, this is a strong signal, right, that we're looking into the concept of what we just discussed, right, that arranging items on a line, right, because we're trying to rank them, but where items are not distinct or items from the same group, right, are indistinguishable. Okay. So having said that, what would the answer be from part for the first question? How many different outcomes are possible? What would that answer be? So here, right, the outcomes would correspond to how many ways you can arrange, right, these lifters on a line, right, but not distinguishing lifter from the same country. So exactly, right, this is 10, choose 3, 4, 2, and 1. Right. What about the second one? Okay, so for this one, right, you want one for the US in the top 3. So out of those 3 positions, right, you choose 1 for the US, right, and 2 in the bottom 3. So again, out of those bottom 3, choose 2, right, for the US, right? which means how many positions do we have left? We have 7 positions left, right? Because you only have the US being placed, and then you have to place the remaining people. So 4, 2, and 1. Is that okay? Any question about this? All right, let's take a look at the last one. Okay. Any input on the answer here? So basically, right, there are 10, I guess, right, distinct countries, right? These are the 4 countries that we care about. But so here we want French and English, right, to be sit next to each other. So there will be a unit by themselves, right? So French and English. All right. There'll be a unit together. So that's fine, right? But we want also Russia and US not to be together. Okay. And if you think about it, right, arranging that is going to be kind of, right, let's say, not easy to visualize because, right, they can be in many places. So this is exactly a case where we want to do it by complement, right? Where we would count the number of ways that both of them are together, meaning French and English delegates together, and, right, US and Russia together. All right. And then, of course, right, so we'll count the number of ways for French and English to be together. And then we'll subtract the way, right, where both of them to be together. Does that make sense? And then we'll get the ways, right, where this is true, but that's not true. Does that make sense? And now, right, once you realize that, then this is like the couple question problem, right? If you fuse French and English, then you have nine countries left, right? Nine units left. So that's 9 factorial times 2. Because, right, these are together, and so there are 8 countries left, right? So 9 factorial times 2 because French and English can be swapped. And then this will be so 6 or 7, right? 7 factorial times 2 squared. So that's the answer. So that's counting by complement. All right. Any question on this? Oh, hold on. Is it 8 factorial or 7? So if we have French and English together, this together, so that's 2. Oh, there's 6 countries left, right? So that's 8 units together, sorry. 8. Not 7. All right, so okay. Any question? All right, so let's stop here today. Well, we have 4 minutes left. You know what? Let me kind of top of the last slide, and then we're gonna call it a day. Okay. So the last slide actually just kind of sum up, right, the combinatorics. So basically, right, we kind of demonstrated this, you know, with the last problem, right, and also in the friends problem, that basically the techniques, right, that we listed above here are not meant to be exhaustive, meaning that there are, right, other occasions where you have to use some other techniques. And the common techniques that we did not list, right, are counting by complement and the inclusion exclusion formula. So yeah, right. So a lot of times it's easier for you to look at, right, the problem where, you know, instead of counting it directly, you have to count the way that it doesn't happen, and then you subtract away from it. So, right, where, you know, you want to arrange the couples together, but that no couple, right, are next to each other. So the complementary problem is how many ways can you arrange 4 couples so that at least 1 couple are next to each other. So again, right, this is not necessarily easier or harder, but when you think about it in this direction, right, that at least gives you some different way, right, to attack the question. Or, right, I guess here, right, this question where you look at, right, the US and Russia, right, you want them to not be together. That's kind of hard to count. So if you count them to being together and then you subtract it away from, right, the case, then it's actually easier. Okay. And so also, as I mentioned, but you know, we didn't see a explicit case, but the inclusion exclusion formula, right? This is where the word or, right, happens. So you can also have count where instead of counting, right, let's say E1 and E2, you count E1 or E2. So in that case, then, you know, you have to use the inclusion exclusion formula, right, to count the number of possibilities. Okay. All right, so I think that's going to be it for the lecture 2, right, and the problem set 2. We're going to move on to the new lecture, lecture 3 next week. Okay. All right. Have a next weekend, and I'll see you next week.
Have a good one. Bye-bye.